Hello everyone, welcome back to the channel. So in this video lecture we shall solve this problem 01 knapsack, which is a very standard interview problem. In this problem we are given two integer arrays, values and weight of size n each, okay, which represents values and weights associated with n items. That means we have some n items, each item has some value and some weight associated with it, okay, and these arrays represents those values and weights. We are also given an integer c, which represents the capacity of the knapsack that we have. Okay, so we have some knapsack or some container in which we want to put some items which we have out of those n items, and what we want to make sure is that the value of those items is maximized. Also, we have to make sure that the sum of weights of those items does not exceed c. Okay, that is the capacity of the knapsack. Okay, so we have to find that maximum value. Fine. The constraints for the problems are the size of the array or the number of items goes up to 1000. The capacity of the knapsack also goes up to 1000, and the values inside those arrays also goes up to 1000. Let's better understand the problem statement using an example. So let's take an example. We have a values array and weight array of 3 items. So we have 3 items here and a knapsack with capacity 50, and we want to put some of these items into the knapsack such that the values of the sum of values of those items is maximized while making sure the weights does not exceed the knapsack capacity. So let's try to make the combinations of the items which we can put in the knapsack. First, we take one item into the knapsack. So we put only single item into the knapsack. The first item that we are putting has weight 10. So we are putting item number 1 into the knapsack, which imparts a value of 60 to it. Okay. Then we are putting item number 2 into the knapsack. It imparts the value of 100. Then we put item number 3 into the knapsack, okay, and the value that we get is 120. Okay, then we put item number 1 and item number 2 into the knapsack. Can we put these items into the knapsack? Yes, we can, because the sum of weights of these items is 30 while the knapsack capacity is 50. So we can put item number 1 and item number 2 into the knapsack. The value will be 60 plus 100, 160. Okay, then we put item number 1 and item number 3 into the knapsack. We can put it because 10 plus 30 is 40, which is less than the knapsack capacity. So put item number 1 and item number 3 into the knapsack. So this will give me a value of 60 plus 120, that is 180. Okay, then we put item number 2 and item number 3 into the knapsack, which is also possible because 20 plus 30 is 50, that is equal to the knapsack capacity. So put item number 2 with weight 20 and item number 3 with weight 30 into the knapsack, and this imparts a value of 220 because 100 plus 120 is 220. Okay, now let's take 3 items at once. Now, can we take item number 1, 2 and 3 into the knapsack? No, we cannot, because 10 plus 20 plus 30 gives 60, which exceeds the knapsack capacity. So we cannot put 3 items into the knapsack. Now, out of all these values, what is the maximum value? It is 220. So that's why this is the answer. 220 is the answer. That means we can put item number 2 and item number 3 into the knapsack, and that will give me maximum value. Okay, so that's the answer for this test case. Now let's try to build the solution for finding this answer. So let's see the intuition to solve this problem. You see, we are taking the same example. We have 3 items. Each has some value and weight associated with it, and the knapsack capacity is 50. So we start with the empty knapsack and from the first item here, and we ask, can we put item number 1 into the knapsack? Yes, the answer is yes, because the capacity of the knapsack is 50 and the weight of the item is 10. So that means this is possible to put item number 1 into the knapsack, but that will decrease the capacity by 10. Okay, so here we had empty knapsack, but now I have knapsack with item number 1 inserted into it. Another option is we do not take this item into the knapsack, because it may be possible that in the final answer item number 1 is not included. Okay, so that is a possibility. So we are exploring two possibilities for each item. Either we take it into the knapsack or we do not take it into the knapsack. Okay, so in case this is not into the knapsack, we skip it and the capacity stays the same. So this was the initial state of the knapsack. Now we have two possible states for the knapsack. The first state says we have item number 1, and the second state is we have empty knapsack. Okay, now let's move to the item number 2 and this state here. The capacity that we have here is 40. Can we insert item number 2 into this knapsack? Yes, we can. So that will give me C minus 10 minus 20. This as the remaining capacity of the knapsack, and here we are not inserting this item into the knapsack. That is second possibility. So for each possible state we are exploring either to take it or do not take it. Okay, 0 1 0 1, so that's why we call it 0 1 knapsack. Okay, then we do same for this state. Here we take the item number 2 into the knapsack, so that will give me C minus 20, and we do not take it into the knapsack. That gives me this. So now we have 4 states here. We have item number 1, item number 2 into the bag. Okay, so first item has weight 10, second item has weight 20. The second state is that we have item number 1 only. That means we have item with weight 10 inside. Then we have third state, that is we have item number 2 inside and it has weight 20. Then final state is we haven't put even a single item into the knapsack and the knapsack is empty. So these are the 4 states. Now let's move again to the first state. Can we put item number 3? Okay, because we have explored all the possibilities for first 2 items. Okay, now we are going to item number 3. Can we put item number 3 into this knapsack? And the answer is no, because the remaining capacity here is 20, because 50 minus 10 minus 20, which will give me 20. So we cannot put item number 3 into this knapsack. Therefore we keep it as it is. Okay, that means we just have item number 1 and 2 inside it. Can we put item 3 here? Yes, we can. So that will give me a capacity of 10 minus 30, because here the capacity is 40, because 50 minus 10 is 40, and we can put an item of weight 30 here. And definitely the another case where we do not take this item as well. Then here, can we put item with weight 30? Yes, we can. That will give me a remaining capacity of C minus 20 minus 30, and another case where we do not take this item as well. So here in this final state, we take the last item into the knapsack, then we do not take this item into the knapsack. So we have explored all the possibilities for all these 3 items. Okay, starting from the empty knapsack. Okay, now each branch gives me a set of values, set of items which I have inserted. So now I have 1 2 3 4 5 6 7 states. Okay, so these are the possible states that we can have. We have to choose that state, okay, where the value of the items that I have inserted is maximized. Here we see the value is 0 because I haven't inserted even a single item into the knapsack. Here the value is 120 because item number 3 is present, so 120. Here the item number 2 is present only, so we have 100, a value as 100. Here the item number 2 and item number 3 is present, so the value is 220. Okay, and here item number 1 is present, so we have value as 60, and here the item number 1 and item number 3 is present, so the value is 180. And finally we have item number 1 and 2 here, that gives me the value 180. Okay, it's 180 and this will give me 160. Okay, so out of all these values, this value is maximized, so it is best to choose item number 2 with weight 20 and item number 3 with weight 30, because it gives me the maximum value. I get maximum value out of this set. Fine, so let's see how we can build a working solution for this problem. Okay, so I want you to imagine a function. Nap stands for knapsack, where C is the capacity and I is the index. Okay, index of the starting item. So it basically the function returns me the maximum value which can be achieved with knapsack capacity C and items from I to n minus 1. So let's say I is this. So this function, if I call it this index, it will give me the maximum value which I can get from this set of items. Okay, so let's see how this function should work, then we will move to the implementation part. So initially I call this function obviously at index 0 because I want to know the maximum value for the entire set. Okay, so this function is called at index 0. Now we have two possibilities: either I push this value into the knapsack, or I do not push the value into the knapsack. If I put into the knapsack, the capacity will decrease by the weight of the item. So this is the weight. This is the weight array basically, and this is the values array. Okay, then this is basically same as we explored the states here, but rather we are writing it in the form of a function, where the function returns me the answer. Okay, so similarly for this I will have the maximum, I will get the maximum value which I can achieve from this set, and the capacity is 40. Okay, and so on. Finally we have all the 7 states at the end when I have explored all the items, and what I have to do is to find the set which has the maximum value. Okay, now how the body of this function will look like. Okay, so we know that at each index I have to call the function 2 times. The first one is the case when I have to insert the item, that will decrease my capacity by the weight of the item, and the second case is when we do not have to take the item, that is the case of 0. So this is the case 1, this is the case 0, and here I call this function again, but I do not insert the item, hence I do not decrement my capacity. I pass the capacity as it is. Here I am decrementing the capacity by the weight of the item. So let's say the capacity is C and the weight of the item is weight I, and then I will take the maximum of the value returned by this function was with this function. So maximum of all these two values. We know that at any index what I have to do is, let's say I want to find the knapsack. When I call knapsack for the index 0 and capacity C, which is the initial capacity, and for the index 0, let's take this index, general index I want to get the maximum value for the set I to n minus 1, where the capacity we have the remaining capacity that we have is C. So here what I have to rely on two things. First, I take the ith item into the knapsack. That means the value is incremented by whatever the value that item holds plus the result that I achieve by calling the function on the next item. But here I have to pass the capacity which has decreased by the weight of the item I'm currently putting in the knapsack, that is weight I, and I am calling the function on the next index. Okay, versus I do not take this item into my knapsack, so I call the function nap with the same capacity because I haven't put any item, but on the set starting from the next index, and I take maximum of these two values, max of these two. So that's the recurrence relation that we have got. So this is a recursive code, this is a recursive solution. So let's see how we can implement this in practice. So this is the code implementation of that recurrence relationship. So this is the knapsack function. It takes in an argument as the capacity of the knapsack, starting index of the item. Okay, so we have this saying that I will give you the maximum value of this set from I to n minus 1. Okay, so this is a recurrence. If I take the value, if ith value is that means if the item number I is taken into the knapsack, then the value of that item is added to the answer and I call the function again on the next index. Otherwise, I do not take this item into the knapsack and call the function into the next item. Fine. So this is the recurrence relationship. So this is the case where the weight of some item I, weight of the ith item that we are currently standing on, is greater than the capacity of the knapsack. In that case, we cannot take that item into the knapsack. That's why we just call the function knapsack for the next index I plus 1. And this is the base case when we have reached the end of the array. That means I have crossed the last index 3. So for that, if I is 4, then I return 0, or I have exhausted the knapsack. That means I do not have the capacity to hold any extra item. Then I return 0. Okay, so this is the recursive implementation for the knapsack problem, and let's analyze the time and space complexity for this code. So you see here that each function is calling at most 2 functions. That means the branching factor is 2. Okay, and the height of this tree can be equal to the number of indices that we have. That means or the number of items that we have, n. So the number of function calls will be 2 raised to the power n. So this is the time complexity. So what is the time complexity? 2 raised to the power n, big of 2 raised to the power n, which is an exponential time complexity, and this will not work for the constraints that we have because n may go up to 1000. So 2 raised to the power 1000 will definitely exceed 1 second, which is the judge limit. Okay, so we have to improve upon it, and we know that to improve upon a recursive solution, what we have to do is to memoize the results. Recursive code, we try to memoize it. Okay, so in the memoization, what we do is we store the results of the computations. That means here you can see that there are redundant function calls. So this function will calculate the result for index number 3, and this function is again called here. Okay, so again called here. Similarly for others. So this function, the computations performed by this function are redundant because I am calling the function 3 times. Rather, what I can do is simply call this function once, and whatever the result this function returns, I will store it in an array. Okay, and when the value for that particular index is required for this set 23, I do not have to call this function again. Rather, I simply return the result that I had stored here. Okay, so that's the process of memoization. In that case, I would not have the redundant function calls. So let's see how we can memoize the results. Okay, so this is the memoization table or the DP table that we have. So this represents the rows represents the weight, while the columns represents the index of the items. Okay, because we know that there are two variables here in the recursion tree which are changing at each level. Okay, so dpij represents the maximum value which can be achieved with weight I and items from j2 and -1. Okay, so that's the dp table that we prepare. So let's see how we can change our recursive code to implement this to implement memoization. Let's see the memoized code. This is the memoization table and this is the memoized code. So this is the DP array is initialized with -1 because this it tells us that whether the result for that particular pair of indices, that means I and j, weight I and index j, is computed or not. If it is computed, if it is not computed, then we would have -1 here. If it is computed, then we would not have -1 here. Okay, so that's why we store -1 so that we can check for that particular pair. Here, if I reach the end of the array, I simply return 0 because I have exhausted the array. Now I do not have any item left. If the result at that particular capacity and index is not -1, that means I have already computed results for this function knapsack for that capacity. Okay, for that capacity C and I, it has been called once. Then I return that result which I have memoized here. Otherwise, it says that if the capacity of the knapsack is less than the weight of the current item that we are standing, then we do not take that item into the knapsack. Rather, we call the function again onto the next index here. Okay, and now we have the final condition where we can put the item or we cannot put the item. We have both the choices, 0 and 1. So in that case, this is the condition where we are putting the value into the knapsack, and this is the condition we are not putting the value. If we are putting, we have to decrease the capacity of the knapsack by the weight of the item we are putting in, and if we are not taking in the item, then we pass the capacity as it is and call the function on the next index, and we store it for this particular C and I in the DP table. Finally, we return our DP array for that C and I. Okay, for that capacity and the index. Okay, so this represents that we are computing the value from I2 and -1, and the remaining capacity of the knapsack is C. Fine. I hope you got the idea how this code is working. Now, how this has improved the time complexity, let's discuss that. You can see that here we have to call the function for unique pair of I and j. Namely, I is capacity, j is the index, or we can say unique C and I pairs. Fine, because if a redundant pair appears, then we would already have the result computed in the array. Okay, so how many pairs do we have? If we have capacity as C, that is given in the problem, and the number of indices that we have are n, then these are the unique pairs that we have for the capacity index set here. So that is the time complexity. So you got what I want to say? We would have unique pairs. Okay, so that's the time complexity. What is the space complexity? Since we are using a DP array of dimensions c cross n, the the space complexity will be big of c cross n. Will this time complexity work for the constraints that we have been given in the problem? And the answer is yes, because the constraints are c goes up to 1000, so 1000 into 1000, because n is also 1000, gives me 10 to the power 6 divided by the number of iterations which are done by the computer in 1 second is 10 to the power 8, which is giving me 0.01 second, which is within the time limit, that is 1 second. Hence it will work fine. So this memoized code is will work for the constraints that are given here. Fine. Okay, so that's all for this video. In the next video we shall discuss the second method of solving the Knapsack problem, that is bottom-up manner, building the solution from the smaller solutions. This was the top-down method. In top-down method, what we do, we start from the top and we break the items into the smaller input size, and whatever the result those functions with the smaller input size returns, we compute the final result from those results. Okay, but in the bottom-up manner, we start from the solution of the smaller problems, and then we build up the solution for the larger problems. And I will also discuss the space optimized approach for this problem, that is Knapsack problem. Here I am using the space c into n, and in that code I will decrease the space complexity by a factor of c. Fine. Okay, so let me show you the code implementation for this problem. This is the implementation in C++. This is the Knapsack recursive function. Okay, and this is the base case. Here I'm checking if the weight of the item is less than the capacity of the knapsack or not. Here we check for the condition of memoization, and this is the recurrence relationship. Fine. And this is the implementation in Java, and this is the implementation in Python language. I have attached these implementations, this code, into the description, so make sure to check it out and stay tuned for more such videos. Thank you.